example 1 on partial differential equation, right? Now, when we started, we said under partial differential equation, we'll be looking at several equations, right? The first one was what? Wave equation. The second one was what? Heat equation. The third one was Laplacian equation and Poisson equation, right? Now, and I told us that we'll be doing 2 questions, right? I said we'll be doing 2 questions. The first one is under wave, while the other one was under heat. Now, the theoretical explanation we had previously, we want to implement it to a given question. Say you are given a question, how do I go about this question? How do I solve this question, right? We are going to implement all what we've learned so far. We said when it comes to wave equation under partial differential equation, by definition, wave equation is a second order partial differential equation used to model the motion of a vibrating system, right? We've discussed all what this means previously, right? Also note that our wave equation and our heat equation can be written in one dimension, 2 dimension, and 3 dimension. But given a question, we will always use 1 dimension, right? So what I'm saying is that I know that this is my wave equation. Say this is the square u over the x square, right? Equals to 1 over c square multiplying the square u over the t square. This is wave equation, right? And our heat equation is giving us the square u over the x square equals to 1 over c multiplying the u over the t. These 2 equations, this is in 1 dimension. When I say 1 dimension, meaning in terms of x, let's relate it to Cartesian coordinates. You know, if this is my Cartesian coordinates, I'm having this as x, right? This is what? Y, and this is what? Z. So by 1 dimension, we are saying that we have the x function alone. What if it is 2 dimension? I'm having x and y. What if it is 3 dimension? What do I have? X, y, z. So let's see how we can write this in 2 dimension, also in 3 dimension, right? Now, from what we have here, say this is equation 1 and say this is equation 2. You agree with me that equation 1 is still the same thing as me writing the square u over the t square, equating that to c square multiplying the square u over the x square, right? By the time we cross multiply, we have this. So this is still the same thing as this saying what? 1 dimension. When it comes to 2 dimension, you are involving the y component. That becomes the square u over the t square, equating that to c square, all into bracket, the partial derivative of the second partial derivative of u with respect to x plus the second partial derivative of u with respect to y, right? Similarly, for our 3rd dimension, same idea, right? I'm having this. This is right? So this is the 2nd dimension. This is the 3rd dimension. Also take note that this 3rd dimension can be represented using the Laplacian operator. When we say Laplacian operator, note that this is what we call the Laplacian operator, and it is always equals to this. Right? Meaning that if this is my 3 dimension, I can still write this 3 dimension as what? The partial derivative, the second partial derivative of u with respect to t equals to this very guy, which is c square, multiplying the what? Laplacian operator. What we have here is called the Laplacian operator. Note that Laplacian operator only works for 3 dimensions, right? The question now is, the same way we represented these 3 dimensions in Laplacian form, can I do that for 2D? No. Can I do that for 1D? No. Why? Because your Laplacian operator must have x function, y function, and z function. So that's how it works. So this is the representation in 1D, 2D, 3D. But generally, given a question, say you want to solve a question, you always use what? 1D equation, right? Now, given this question says that, okay, looking at this question, how do I interpret question? What's my ability in interpreting question? That's the first thing, right? Given this question, first thing first, identify is this question under wave equation or its equation? If this is wave equation in partial differential form, and this is its equation in partial differential form, I'm not giving this question first thing first, doing comparison. Is this question under wave or it? It is wave. Observe that both the left hand side and the right hand side, they are second order differential equation, right? Which is the wave one. But for your it, the left hand side is the second order, while the right hand side is what? First order. So given this question, I'm relating all what we know as far as wave equation is concerned to this very question. But note that both wave equation and its equation, they are synonymous. They are they are similar. Nothing is changing, right? Now with this, let's solve this question using a graphical illustration relating it to what we said previously, right? Now, now from here, all right, now I said in the introduction class, I said that there are some terms we need to be familiar with, right? I said the first one is we understanding the definition, right? And from that definition, we've seen that our wave function is in terms of two functions, which is what? X and t. Where x is the space function, where t is the time function. So we are saying that we have u as a function of x and t, right? Right? What's the idea behind this? The idea is that what we have here, we are going to convert this partial differential equation to what? Ordinary differential equation. Where you are going to have two equations. The first one in form of x, where the other one in form of what? T. But these two equations must represent a wave equation. And when we say wave equation, meaning a sine and cosine equation, right? So now, let's say you are giving this, you want to understand this boundary condition. You are giving this boundary condition, and we are giving this initial condition. Let's do a graphical illustration, understanding this boundary condition and this initial condition. Now, consider this. Let's say you have this. Let's say you have this. Let's say you have this, right? Now, from here, this is x. This is x, right? And this is fixed. This end is fixed, and this end is also fixed. Hope you agree with me. I gave you guys a practical illustration the other time, saying that you have a string, and you apply a force on this string. By the time you apply a force on this string, what do you observe? You will notice that vibrations will occur, right? Let's say this is the first vibration, this is the second vibration, this is the third vibration, this is the fourth vibration. All this vibration makes up what we call what? Wave. So we are now saying that initially, this is the fixed end, this is the second end. But the question now is, will there be vibration at this first fixed end? No vibration. Why is there no vibration? It is fixed. Similarly for this other end. Back to your boundary condition. How do you interpret this boundary condition? Looking at this boundary condition, this is where all the work slides on. Looking at this boundary condition, you want to interpret it, right? This boundary condition, you are going to do comparison with the general form of your function. We generalize it that u is always a function of x and t, right? I'm now giving this first boundary condition. What this first boundary condition is saying is that by the time you equate this very guy to this, meaning u as a function of 0 and t, this is the first boundary condition. The second boundary condition, we are having something of this nature, implies u open bracket 2 and t, right? Now with this, doing comparison from the first one, x is equals to what? 0. X is equals to what? 2. So what that means is that your vibrating system in this case, the total length is what? 2. Where the initial end is what? 0. Of course, if you always start from 0, then it's going to end at a particular value. But in this case, it is ending at what? 2. So this is how you interpret boundary condition. So from what we have here, we are saying that at this very end, I'm having u all into bracket 0, comma what? T equals to what? 0. I'm also having what? U all into bracket 2, comma T equals to what? 0. In this case, we are giving that the boundary conditions are equal to 0. How I'm communicating? Given directly from this question, we are told that this first boundary condition is equal to 0. This second boundary condition is equal to 0. In some cases, it varies. It's not as if it's a constant value, right? But just understand how it works. What if I'm having 4 in this case? What does it mean? My first one becomes what? This is equals to 4. This is also equals to what? 4. But commonly, we always see 0. We always see 0. We always see 0, right? So let's proceed. Any questions so far? Yeah, we are going to, earlier I said, once we've gotten our wave equation, you notice that we have arbitrary constants, meaning A, B, C, and D. So this boundary condition, your x function is the space function, your t is the time function, and you also note that this space function, you have A and B present in it, while your time function, you have C and D present in it. So the aim of this boundary condition is that you want to know the value of A and B. You want to know the value of what? A and B. How do you get A? Apply this first boundary condition. How do you get B? Apply the second boundary condition. Meaning you found the value of A and B. Similarly, I want to know C and D. How do I get it? Apply your first initial condition, then apply your second initial condition. So that's it. That's what we are. Okay, now with that question also. Now this is it. We are going to what we'll be practicalizing it, right? Now let's say this is A. Let's say this is A. Imagine we've gotten those values, that wave equation. Now say this is A, say this is B. There's what we call engine value. I said it previously. Each engine value has their engine function, right? But this is the whole concept of engine value and engine function. Now in this case, we already know that this is my starting point. No vibration, right? Meaning when x equals to 0, A is what? 0. That's the meaning. Say this is A, say this is B. We want to do a practical explanation now. What brought up about engine values and engine vector, right? Sorry, engine values and engine function. Now, say this is A, say this is B. At this A, I'm having x equals to 0. When x equals to 0, A is also 0, right? Mathematically, when x equals to 0, A is also equals to 0. With what I have on this board, right? Now, at this point, x equals to what? 2. If x equals to 2, what does it mean? We've represented this place as A. We've also represented this one as what? B. So I'm saying that for this one, I'm saying x equals to 0. I also have B. I also have A equals to 0. Why am I having A equals to 0? From the boundary condition, we've been told that giving this equated to 0. Let's say this was 4. Meaning when x equals to 0, A equals to what? 4. Are you getting it? But back to the question, I'm having 0. Meaning when x equals to 0, A equals to 0. Using that same idea to answer this, when x equals to 2, B will be what? 0. But is it possible? It is not possible. Why is it not possible? Because B is the last end. If B is 0, meaning wave has not occurred, oscillation has not occurred. Are you getting me at all? From what we have here, we said x equals to 0, A is also equals to 0. Using the same idea to answer this, meaning that when x equals to 2, I'm having what? B equals to 0, but it is not true. B cannot be equals to 0. B is not equals to 0. True or false? True. The question now is, why is B not equals to 0? Because from here, at B, I'm having x equals to 2, meaning the total span, the total length. This total length, wave oscillation would have occurred before getting to x equals to 2. I'm not saying for the total length, which is B is equals to 0. Does it make any sense? No. If I'm saying B is equals to 0, it means no oscillation has occurred. And if no oscillation has occurred, we've not done anything related to wave. But you see what this means. You see what it means. So if that being the case, that we know that B cannot be equals to 0. But at the same time, we know that there will not be wave at this particular end, right? So what if we generalize an equation, say N? Okay, what if we generalize an equation, say lambda, meaning wavelength? Lambda is equals to m pi over n. The total length is what? 2. For n, take your n as 0, 1, 1.5, 2, right? 0, 1, 1.5, 1.7, 1.82. Since the total span is what? 2. Meaning at 0, by the time you use this formula, when n equals to 0, your wavelength will be what? 0. Are you getting me at all? Will there be oscillation at this point? No. Will there be oscillation at this point? No. At B, will there be oscillation? No. It is fixed. It is fixed. Will there be oscillation here? No. Why? Because it is fixed. Will there be oscillation here? No, it is fixed. But within the span, there will be oscillation, right? I'm not saying that. Let's say we have this equation where n represents the distance. Now, when n equals to 0, it is obvious that oscillation does not occur, right? I'm having 0. When n equals to 1, there will be oscillation, meaning you have a value for this wavelength. When n equals to 1.5, you also have a value. When n equals to 1.7, you also have a value, right? But when n equals to 2, we have a value. Will there be oscillation? No oscillation. You don't have when there's no oscillation, meaning lambda becomes what? 0. Are you getting me? Lambda becomes what? 0. So this is the idea of engine value. Engine value, since we said B is not equals to 0. B is not equals to 0. We know that B is not equals to 0. But then, we also know that practically, there's no oscillation here. So instead of we saying B is equals to 0, we can, what if we have an equation that give us the oscillation at that point? So this is the engine value. This is the idea of engine value. But you understand what I'm saying better. So let's proceed. So that's the idea of boundary condition and initial condition. So in essence, I'm saying that boundary condition help us to know the two constants, which is A and B. Then initial condition help us to know the other two constants, which is what? C and D, right? So let's continue. We've been able to identify that this question is under what? Wave equation, right? Because that U is a function of what? X and T. U is a function of X and T. You know, this is your partial differential equation. This partial differential equation, you want to turn it towards ordinary differential equation. How do you go about it? From what you have here, find the partial derivative, then substitute back into this partial differential equation. So meaning from here, I'm having two differential terms, right? The first one is what? The second partial derivative of U with respect to X, and the second partial derivative of U with respect to T. Meaning I'm going to evaluate this partial derivative from this general solution or from this equation, right? Now, you know the reason why we are differentiating? We are differentiating so as to get to ordinary differential equation. You know, the whole idea is that this partial differential equation, we want to change it to what? Ordinary differential equation, right? Now, from here, from U equals to xt, meaning U is a function of X and T. Let's differentiate. We differentiate, meaning the partial derivative of U with respect to X. What do I have? X prime multiplying T, right? Then, the second partial derivative of U with respect to X. What do I have? X prime prime T, right? With respect to T, meaning the partial derivative of U with respect to T, this becomes st prime. The second partial derivative becomes what? xt prime prime, right? xt prime prime, right? Now from here, let's substitute values into our general partial differential equation. Substituting values, it becomes what? Second partial derivative of U with respect to X. What do we have? We've gotten this, right? So I'm having X prime prime multiplying T, equating that to what? 1 over 16 multiplying what? Multiplying X T prime prime, right? So this is equation 1. If this is equation 1, you observe that equation 1 contains only function X and function T. So what we are going to do in this case is that separate the function of X from function of what? T. Meaning you want to implement the idea of separable variable. So meaning from equation 1, implementing separable variable, it becomes S prime prime over X equals to T prime prime equals to 1 over 16 multiplying T prime prime over T, right? Moving on, this can be written as X prime prime over X equals to 1 over 4 square multiplying T prime prime over T. Take note that, or observe that 16 has been written as what? 4 square. The question is why? We related it to the standard wave equation. Because that we've said that the square u over the x square is equals to 1 over c square multiplying the square u over the t square. Meaning in this case, c is what? C equals to what? 4. Given any question, always try to put it in this format. Always try to write it in this nature. So that's what we did here. Now, from what we have here, say this is equation 2. Right? Say this is equation 2. From here, I want to know the function of x, and I want to know the function of what? T. From this u being a function of x and t, the whole concept is that I want to know the function of x, and I want to know the function of what? T. Meaning, before you can know the function of x and t, you must have a differential equation. Right? Say you want to know the function, you want to know the function that has been differentiated. You'll be given that function in terms of what? Differential form. This is what I'm saying. Let's take it back to ordinary differential equation. Say in ordinary differential equation, you are having the square y over the x square plus 2 dy over the x equals to sine x. You know, we'll be giving this question. Question will just be given. What are we meant to do, or what are we asked to do? We are asked to find function y, right? Hope I'm communicating. Are you getting what I'm saying? Yes. Given this function in ordinary differential equation, what's the idea? The idea is that I want to know function. I want to know the function of what? Y. Meaning that in this case also, say this is u being a function of x and t. You are interested in knowing the function of x, and you are interested in knowing the function of t. I'm not saying that before you can know the function of x and you know the function of t, you must have a differential equation. Meaning you must have a differential equation expressing x, and you must have a differential equation expressing t. Up to what we have here, this is how you get that differential equation. Now, how do you get that differential equation? You are going to equate equation 2 to a constant. You equate it to a constant of your choice, right? You are going to equate equation 2 to a constant. But in this case, the constant is what? K. Where k is less than 0. You know why k is less than 0, right? Are you getting me at all? I said, in this case, you are going to equate that constant to what? K. So meaning we are having, meaning from equation 2, I'm having x prime over x equals to k, right? And I'm also having 1 over 4 square c prime over t equals to what? K, right? This first one will give us the differential equation of x. This second one will give us the differential equation of what? T. Now, from what we have here, cross multiply. By the time we cross multiply, this becomes s prime equals to kx. Bring kx to the other side. This implies x prime minus kx equals to 0. Say equation 1. Say equation 1, right? Same idea. Cross multiply. By the time we cross multiply from this second one, it becomes t prime equating that to 4 square multiplying tk, right? Bring this to the other side. What do you have? T prime minus 4 square multiplying tk. Equate that to what? 0. Say equation 2. Right? Meaning from equation 1, I can know the function of x, and from equation 2, I can know the function of t. Me knowing the function of x and function of t, meaning I've gotten the wave equation, meaning I've modeled the equation for that vibrating system. That's what it means, right? But take note that from here, I didn't know that I would get function of x, and I didn't know that I would get what? Function of t, right? And the whole concept is that wave equation, by wave equation, oscillation has occurred. Are you getting that? You know, when we say wave, meaning oscillation has occurred. Meaning in this case, does this equation satisfy a wave equation that will have your oscillation will occur? Are you getting that? Now, for me, I said when it comes to wave, all we are saying is that oscillation has occurred, right? Meaning we have oscillation, we have vibration. From what we have here, we know we get the function of x. We also know that we get the function of what? T. But the question is, this first equation, does it satisfy a wave equation that will make our oscillation to occur? Are you getting me? Similarly, does this second one satisfy a wave equation that will make our what? Oscillation to occur? Now, how it works is that for these two equations to satisfy a wave equation whereby you have your oscillation occurring, you are going to assume k less than 0. You are going to what? Assume k less than 0. So when we say k less than 0, meaning you are saying k is equals to negative p squared. We are saying that k is equals to what? Negative p squared. Right? Assume any value of p. Let's say p is equals to 4, meaning negative 4 squared, which is what? Negative 16, is less than 0. Let's say p is equals to 10, meaning negative 10 squared, which is what? Negative 100, is less than 0. So meaning that oscillation will occur when k is less than 0. When k is less than 0. So take note of that. So if that being the case, anywhere you see k, substitute what? Negative p squared. Meaning I'm substituting negative p squared into equation 1. I'm also substituting negative p squared into equation 2. Normally I would have said that these are my, are you getting me? Now also add this or note this. Why am I doing this? I'm doing this because when we use different textbook, you can see it represented in different way, right? Normally I would have said that my constant in this case is equals to negative lambda. Are you getting me? I would have said that this constant, okay, this is it. This is what I'm saying. Now from here, I'm saying that we want to have an equation that will satisfy a wave equation for oscillation to what occur, right? So we are going with this. But in some cases, you are going to see it as k equals to lambda, which is still equals to negative lambda squared. Just have it in mind that, you know, in this case, k is still lambda. Lambda is still negative square. All of them are still a constant, right? All of them are still a constant. But you see, you get to what I'm going to. You see the reason why I said, let's go with this, right? Let's proceed. Meaning from here, substituting k as negative p squared, equation 1 becomes what? X prime prime plus p squared multiplying x equals to what? 0, right? This is our new equation 1. Then our new equation 2, we have what? T prime prime, right? Plus 4 squared multiplying p squared multiplying t equal that to 0. Say equation 2. Any questions so far? So these two equations satisfy a wave equation where oscillation will occur. And we know that our wave equation always have sine and cosine as a function. Meaning a wave equation is always expressed in terms of what? Sine and cosine. So from what we have, meaning yeah, I've substituted directly. Okay, this is it. From here. Yeah, okay. Okay, let me even work it out. Because some people might not understand. Now from here we said k equals to negative p squared, right? If k is equals to negative p squared, I'm having x prime prime minus kx equals to what? 0. Meaning x prime prime minus all into brackets negative p squared multiplying x equals to 0. I then have s prime prime plus p squared multiplying x equals to what? 0. This is our new equation 1. From equation 2, same idea. I'm having t prime prime minus 4 squared multiplying t multiplying k equals to 0. Substitute k as negative p squared. This is this, right? T multiplying negative p squared. Right? Any question? So this is our new equation 2. So what that means is that this first equation and this second equation satisfy what? A wave equation. And if they satisfy a wave equation, meaning oscillation will occur. If you substitute k less than 0, you have a wave equation. When you substitute k greater than 0, you have an exponential equation. When you substitute k equals to 0, you have a linear equation. You have a linear equation, right? Yeah, it is constant. These are how you work it out. All of these are constant. Though that's what I'm saying. I said in some cases, we are using k equals to negative p square. We are using k equals to negative p square. You might decide to use k equals to negative lambda square. Are you getting me? You might decide to use k equals to negative lambda square. If k becomes negative lambda square, meaning in place of p, you have lambda square. You also have lambda square here. But I'm using the same idea. We are still going to get to the part of lambda square. If you check some textbook, you see this. If you check some, you see this. Right? So that's why I'm taking it from this first place. But you see what it means when I say lambda square. So let's proceed. Now from here, this is equation 1, this is equation 2. These two equations satisfy a wave equation. And when it satisfies a wave equation, it means what? Oscillation will occur, which is our main interest as far as this topic is concerned, because we said wave equation. We want to model the motion that occur in a vibrating system, right? Now, moving on, this becomes what? For this first one, x function becomes what? Earlier we said we have u being a function of x and t, right? And we are interested in knowing x function and t function. From this first differential equation, I can get x function, right? And from this second differential equation, I can get what? T function, right? So we need to know that every solution or every differential equation has their own solution. For each differential equation, they have their own solution. Now, doing comparison between this first one and second one, is there any difference? Is there any difference? There's no difference. When I say looking at it in terms of differential form, this is x prime prime, this is x, this is t prime prime, this is t. In some cases, you have t prime and you have t, meaning the solution for that one will be different from this. Are you getting me at all? And that's what differentiates between wave equation and its equation. In case of its equation, you have your first equation as this, meaning this will give you the function of x. While with this, you will get the function of t. But in wave equation, they are the same. But its equation, you have the first one as this, you have the second one as this. That's all the difference between wave equation and its equation. So I'm saying that every differential equation has their general solution. So by the time you observe this first one and this second one, you will see that both of them, there's no difference. They are similar. Meaning that the solution for this will also be synonymous to this, right? So for this first one, meaning x as a function, is equals to a cos px plus b sine px. Observe that p square x becomes the angle, right? This is the angle px. So meaning in this case, what will be your angle here? 4pt. That will be your angle, right? Now, this is your x function. Then your y function. Your y function will be what? That will be c cos all into bracket 4 multiplying p multiplying t, right? Plus d sine all into bracket 4 multiplying p multiplying t, right? Now, back to what's that? Just note that your angle, this is where you obtain your angle from. Okay, this is t, true. Thanks. So this is t. From this, now, from this differential equation, we want to know x function. This is x function. Meaning, if you see differential equation of this format, or of this nature, this is the solution to it, right? If you see differential equation of this nature too, this is the solution to it. Are you getting me? By the time you check these two, there's no difference between them. The difference is just the function. In this case, I'm having x. In this case, I'm having t. And the constant here is what? P square. The constant here is what? 4 square p square. So this is the solution to this differential equation. For every differential equation, they have their own solution. So meaning I've gotten x function and I've gotten what? T function. And you observe that this x function, we have it in form of what? Cosine and sines. Meaning wave equation. When we say wave equation, oscillation has occurred. In a case whereby we are not having sine and cosine, meaning no oscillation has occurred. So that's how it works. Now from here, what does it mean? It means from this general solution that we stated previously, saying u as a function of x and t is equals to x multiplying t. You already know the function of x, right? Which is this. I already know the function of t, which is this. Then substitute. By the time you substitute, that's your wave equation. That's your wave equation. But you have to solve the value of a, b, c, and d. You solving a, b, c, and d will take us back to what I said previously. You are going to solve a and b using the boundary condition, and you are going to solve c and d using the initial condition. Looking at what we have here, this is our boundary condition. This is my first boundary condition. This is my second boundary condition. And we know how to interpret this boundary condition. We are saying that x equals to 0. We are saying that our equation is equals to 0 when s equals to 0, right? We are also saying that our equation is equals to 0 when s equals to 2. But you see what I'm saying? You see what I'm saying? But up to this level, any question? No question. No question. Right? Now, back to this. You know, in this case, observe our angle. This is cos px, right? This is what? Cos 4pt. In some cases, you see it as lambda x. You see it as what? Lambda x. So let's go with lambda x. I purposely did this just to understand how it works when you have your angle in form of p and when you have your angle in form of what? Sine, right? But I would advise that up to this level, you are still doing the same thing, but just to follow the, like, let's say sine convention, just to follow a particular order. Let's change this our angle to what? Wavelength, to lambda, right? From this angle, observe that this angle, I'm having my angle as what? Px, and I'm having the first one as what? P multiplying x, the other one as what? 4p then t. But we are dealing with what? Wave equation, right? You know, let's say we are dealing with wave as a topic. You know, when it comes to wave, it has different parameters to be used, right? Let's take it back to this. Let's say graphically, this is my wave, right? This is the amplitude, right? This is A, where this is the wavelength, right? This is correct, right? This is the amplitude, this is the wavelength, this is crest, right? So to follow that sign convention, meaning when I say convention, meaning we want to follow the parameters, just like we're doing differential and integration now. You know, the mostly used function is y and x, right? It's not as if you cannot use another function, meaning p and t, but mostly used is what? Y and x, meaning that's the commonly used variable. So in this case too, you know, your wavelength cannot be represented as, is it possible your wavelength should be represented as t? In wave, it is not possible. Or is it possible for your wavelength to be represented as x? It's not possible. So meaning that up to this level, we are trying to like follow the standard parameters used in wave. You know, the topic itself is what? Wave equation. So in place of this p, I can represent it as what? Lambda. Are you getting me? In place of this p, I can represent it as what? Lambda. Or better still, you would have started with k equals to negative lambda square. It's still the same thing. It's still the same thing. Are you getting me at all? You know, what we did was that we said k is equals to negative p squared. K equals to negative p squared. And we are still converting it to what? Lambda. So it's either you start with negative p squared, then later on change it as lambda, or you should just go directly with this. Any question? If it was negative lambda square we use, then in this case I'll be having positive lambda square, right? I'll also be having positive lambda square. Then you writing your solution, it will be a cos lambda x plus b sin lambda x. This one too will be what? C cos 4 lambda t plus d sin 4 lambda t. So that's it. But I just did the first one just to understand that not necessarily you equate it to lambda always, because some textbooks use it vice versa. So meaning from here, I'll be changing my angle, saying this is what? Lambda x. This is what? Lambda x. And this is what? 4 lambda t. And this is also what? 4 lambda t. Any question on that? No question. So from here, Recall that we said u as a function of x comma t is equals to what? X multiplying t. And we've gotten x to be this, right? And we've gotten t to be this. What do? Substitute. By the time we substitute, you are saying that u being a function of xt is equals to what? All into bracket a cos lambda x, right? Plus b sine lambda x, right? Plus, okay, times multiplying b cos 4 lambda t, right? Multiplying c cos 4 lambda t plus d sine 4 lambda t. Close the bracket. Any question? So this is our wave equation. But then we want to solve the value of what? A, B, C, and D. We want to solve the value of A, B, C, and D. But note that we always reference back to what we've got in here, because this is the general wave equation for this question. We always reference to it. Meaning, let's say you've gotten A equals to 0. Substitute the value of A that you've gotten into the general equation. Let's say you've gotten A equals to B. Substitute the value back into the general equation, right? Now, from here, what we are going to do is that open this bracket. Open this bracket. When I say open this bracket, meaning that multiply this with this. Meaning multiply a cos lambda x with this, right? Plus b sine lambda x with this. So let's do that. So meaning I'm having u as a function of x and t is equals to all right, now from here, let's continue. Now we already got here. We said this is x, this is x, this is what? T. Then the next step is what? Open this bracket, meaning A multiplying this, B multiplying this. By the time you open up this bracket, you then have this, right? Now from here, what you want to do is that you want to solve the boundary you want to solve the arbitrary constant, meaning you want to solve A, C, B, and D, right? Now, how do you solve A, B, C, and D? The first step is what? Apply boundary condition. Apply what? Boundary condition. Now, let's say we have this as our illustration. Let's say you have this as our illustration. Given from the question, the first boundary condition, you are giving that when x equals to 0, equate your wave equation to what? 0. That's the first boundary condition. The second boundary condition is what? When x is equals to 2, equate your wave equation to what? 0. Are you getting me? So meaning that, let's say this is A, let's say this is B, right? Now from here, apply this boundary condition to this first step, Are you getting what I'm saying? Are we following?
Yes.
Now from here I said this from the question, given from the question, this is the first boundary condition and this is the what, second boundary condition. After distributing this bracket, apply this condition to this first step or to this first expression. You know, this is an expression. This is the first expression. This is the second expression. So meaning these two boundary conditions. Apply these two boundary conditions to this first expression, right? Now we're doing that. What do we have? We are saying that when x equals to 0, equate your wave equation to what? 0. So meaning I'm having u all into bracket 0 comma t is equals to a cos all into bracket lambda multiplying 0, right? Which is still 0. Open bracket c cos 4 pi t 4 lambda t plus d sine 4 lambda t. Any question on this? I said once you distribute that bracket, meaning once you open that bracket, once you expand that bracket, say this is your first expression and say this is your second expression. Now apply this first two boundary condition to this first expression. What it means is that substitute x equals to 0. Anywhere you see x into in this first expression, substitute it as what? 0, right? Then I'm having a cos lambda x. I've substituted x to what? 0. That's why you're having it as lambda dot 0. Where you are repeating this one. Do we have any function of x here? No. So you repeat it. What do you say? Right? And this boundary condition is telling me that this is equals to what? 0. Any question? This is the boundary condition. Once you substitute x equals to 0, equate it to what? 0. By the time you equate it to 0, what do you have? Because 0 is what? 1. So you are having u as a function of 0 comma t equals to a, right? This gives me cos 0. Cos 0 is what? 1. 1 multiplying a, you still have what? A. Then you'll be left with this, right? Meaning c multiplying cos 4 pi t plus d sine 4 pi t, right? Okay, lambda t, equating that to what? 0. Now from here, I want to know the value of a. It implies what? What will be the value of a from what we have here? A is equals to what? You know, this is the left hand side, this is the right hand side. We having this mathematically, what does it imply? A is equals to 0. Yes. When we have something like this, mathematically, it implies a equals to 0. If you divide both sides by this, you have 0 by this, which is still 0. It implies a equals to 0. And how do we know that a is equals to 0? Divide all through by this, you have 0 by this, which is still what? 0. So meaning that we've gotten a to be what? 0. Now, I said we've gotten our general wave equation, right? When we got our general wave equation, this is what we got. Any question? You know, this was the x function and this was the what? T function. Now, the next step is what? Find the constant, meaning you want to find a, b, c, and d, right? Now, before finding your constant, multiply this, expand this bracket. When we say expand this bracket, this multiplying this, you have this first expression, right? This multiplying this, you have this second expression. Now, your first boundary condition, given from the question, your first boundary condition, you are having that when x equals to 0, equate your wave equation to 0. That's what we did. When x equals to 0, equate your wave equation to 0. Meaning that if this is my wave equation, but we are using this first expression, let's say this is 1, let's say this is 2, right? Are you getting me?
Yes, sir.
Say this is 1, say this is 2. But if you want to apply your first boundary condition, apply it to this first one. Apply it to what? To this first one. Or better still, identify the one that has a with it. Are you getting me? Identify the one that has a. You know, from this first one and this second one, this one is having a. You know, you want to calculate a. You calculating a, you are going to make use of this one. Why are you using this one? Because this one has what? A. Let's say you are using this one. You will not get a. You'll be getting another value. So meaning once you separate this like this, identify the one that has a and this one has a. If this is having a, meaning apply the first boundary condition to this first expression. And by the time we do that, we end up getting a to what? 0. If a is 0, your next step is to substitute the value of a that you've gotten into the original wave equation. So if this is the original wave equation, I've gotten a to be 0. Anywhere I see a, substitute 0. By the time you substitute 0, you'll be left with this, right? You'll be left with b all into bracket this, right? Meaning I'm having this. You having this, substitute the second boundary condition into what you have here. Are you getting me? With what you are left with, when you've gotten your a equals to 0, substitute the what? Second boundary condition. Meaning that you are substituting your second boundary condition into this wave equation. Using the same idea. How do you write it out? You are saying that so you doing that, what you are saying that you all into bracket 2 comma t equals to, don't forget that you are using this, right? Meaning anywhere you see x, substitute what? 2. Meaning you are having b sine what? B sine all into bracket 2 lambda all into bracket cos, okay, c cos all into bracket 4 pi lambda t, right, plus d sine 4 lambda t. Any question on that? Can you see how it works? So meaning that this is what you are going to use to get your b, or this is our second boundary condition. And by second boundary condition, we are saying that equate it to what? 0. Equate it to what? 0. Now the question is, easily for us in this case was okay, now the way we did the first one, we said from the first one it was easy for us saying a equals to 0 directly, no stress, right? The same way we say a equals to 0 for the first one, can we also say that b is equals to 0? Yes. Can we say that b is equals to 0? Can we say that b is equals to 0? Why? Yeah, because practically b cannot be 0. If b is 0, meaning oscillation has not occurred. This is what we are saying. Let's say graphically you have this. Let's say you have this. Let's say we have this. This is our oscillation, right? This is our oscillation. This is what? This is a, meaning x equals to what? 0. This is b, meaning x equals to what? 2, right? Now, when x equals to 0, a equals to 0. Agreed, right? When x equals to 2, b is equals to what? Will b be equals to 0? No. B can't be equals to 0. The question is why? If you are saying b is equals to 0, meaning this oscillation that you are seeing here, it has not happened, it has not occurred. Meaning no oscillation. An oscillation must occur. So you are doing wave equation. Are you getting me at all? So, and this a and b, we have it at the what? Fixed end. A occur at the what? Fixed end. And b also occur at the what? Fixed end. So instead of we saying b is equals to 0, you are saying that b is not equals to 0. You know the reason? The reason is because you saying b is equals to 0, you are saying that oscillation has not occurred, right? And at the same time, I know that no vibration at b equals no vibration at this b, no vibration at this b. Meaning, me knowing that there's no vibration at this b, I have to get it. Are you getting me at all? I know that there's no vibration at this b. When there's no vibration, what does it mean? Meaning 0. Are you getting me? No vibration at this b. When there's no vibration, meaning 0. So meaning that I have to generalize a formula that I'm going to use, or that will show me that I'm having 0 here, which shows that there's no vibration. And that's what we call the engine value. That's what we call what? Engine value. So by engine value, when you substitute x equals to 2, you get 0. You getting 0 at x equals to 2, what does it mean? No vibration has occurred at that point, which is what? B. Are you getting me? So now, up to this level, since we said b is not equals to 0, agreed. B is not equals to 0. Is that agreed? Alright. Now, if b is not equals to 0, if b is not equals to 0, b is not equals to 0, right? Now, this is your absorption. You are going to say that sine 2 pi is equals to sine n pi. Right? You know, this is what I'm having. This is what I'm having. I'm having b sine, all into bracket, 2 lambda is equals to what? Sine, all into bracket, n pi. We are bringing this, it is pi. We are bringing this from wave. This idea is brought from wave. Now, we're looking at this. You are saying that b is not equals to 0, right? If b is not equals to 0, meaning that this sign will cancel out, right? You'll be left with what? 2 lambda. You'll be left with what? 2 lambda equals to what? N pi. Now, make lambda, what do you say? B not equals to 0. B not equals to 0. Sign cancel sign. 2 lambda n pi. B not equals to 0. This is how it works. B not equals to 0. From here, make lambda the subject of the formula. What do you have? Lambda is equals to what? N pi over 2. And this is our engine value. Engine value varies. You know they constant though. So this, what's that? What's that? You know the assumption is based on wave. Sine n pi. Sine n pi. What? Yeah. Yes. Because it's not equals to 0. B is not equals to 0. When we say B is not equals to 0, the idea is that we want to know the oscillation at B. So since we want to know the oscillation at B, I need a formula to do that. So we're saying I need a formula to do that. That's the formula which is called the engine value. So this lambda equals to n pi over 2 at B. What value of x? 2. Meaning by the time you substitute 2 equals to this equation, you end up having 0, which has shown that at B, no oxidation. Why is there no oxidation? Because you got 0. So from here, if B is not equal to 0, the assumption is that B sine 2 pi is equals to sine n pi. This is still coming from wave. It's still coming from wave. So now from here, we are saying B not equals to 0. 2 lambda is equals to n pi. Now make lambda the subject of the formula. You then have what? N pi over 2. And this n pi over 2 is called the engine value. This n pi over 2 is called the what? Engine value. It is called the what? Engine value. Now the question is, what are we using this engine value to obtain? Or what am I doing with this engine value? This engine value, you are going to substitute it back to this equation. This engine value that we've gotten, you substitute it back into this equation. You know, I said each engine value has their what? Engine equation. Are you getting me? Each engine value has their what? Engine equation. Now, meaning that anywhere you see lambda, anywhere you see lambda, what do you substitute? N pi over 2. I'm coming. Hello, now let's, because of time. Now for me, I said now up to this level we've gotten our engine value, right? Now this engine value that we've gotten, we are going to substitute back into this original equation as well. Now what we did, this is it. What we did was that initially when we got our original equation, we said from this original equation I want to know what A and B. I'm going to get my constant, which are what? A and B. How do you get A? Use the first boundary condition, right? Using the first boundary condition, we end up having what? A equals to 0. Then how it works is that we substituted A equals to 0 into the original equation. We got this, right? Right? Then now, from this guy, we applied second boundary condition. By second boundary condition, we know that B is not equals to 0, right? If B is not equals to 0, we got engine value. You know, the idea of engine value is coming from B not equals to 0. Now, from this engine value, what does it mean? Substitute it back to what you have. Substitute it back to this. Are you getting me at all? Can you see that it is following like a stage? Same stage. You know, initially when we got a equals to 0, we substitute back into the original equation. We got this. Now, instead of which to get b, you know, normally I would have gotten b, but we said b can't be equals to 0, so we got engine value. This engine value substitute back. Had it been it was b that we got, what are we going to do? We'd have substituted back also, but in this case we got engine value. So by engine value, substitute back into this equation. Are you getting me at all? Now, you substituting is, what do you have? You then have, what do you have? Meaning u as a function of x and t is equals to what? B sine, where your lambda, your wavelength is equals to m pi over 2, right? So let's do that together. What do I have? B sine, all into bracket, m pi x over 2, right? Any question? All into bracket. Okay, also note that from here, I'm having 4 pi t, right? Which is still the same thing as 4. Okay, from here I'm having 4 pi. Sorry, where is it? I'm having 4 lambda t, right? Which is still the same thing as 4 all into bracket n pi over 2 divided by what? T, right? Are you getting that? What we are doing is substitution. We want to substitute lambda equals to n over 2 into this equation, right? Meaning I'm having u as a function of x and t equals to b sine all into bracket n pi x over 2, right? What was that? No, not this. I'm saying this. You are not following us. This is what we used to get. You know, from here, I want to get b. But we've seen that b is not equal to 0. If b is not equal to 0, you get engine value. If this is your engine value, substitute this engine value into this. You know, it's following same procedure. Earlier, when we got a, we substituted a into the original equation. Then we are left with this, right? Now we've gotten b. We've gotten engine value, which is our b in this case, as m pi over 2. Meaning you are still going to substitute back into this. It's not as if you substitute it into this, right? So we're doing our substitution. We have this. I'm not saying that. Take note that 4 pi lambda, let's bring it out. Meaning I'm having 4 all into bracket, your wavelength, which is what? M pi over 2 multiplying 2. Then this will cancel out. I'll be left with what? 2. So meaning anywhere I see 4 lambda t, what do I have? 2n pi t. So moving on with our substitution, what do I have? I'm having, what do I have? C cos, right? Plus what? Plus d sine 2, right? That's all. Yeah. No, not this. You are not equating to this. You are not substituting to this. You are substituting to this. This is the general wave equation. You know, this one, what we have here, this is not general wave equation. There's about the lambda equals to n pi over 2. This is what we are following. Let me clean this. This is what we are following. From here, I'm having b sine lambda x. What's lambda? N pi over 2. Meaning n pi over 2 times x. Yeah, when s is equals to 2, we got engine value. You know, when s equals to 0, we got a, right? When s equals to 2, we are meant to get b. But we see that b can't be equals to 0. So we got engine value. Yes, we are not changing it here. We are s equals to, yeah, we are. This is the final wave equation now. This is the final wave equation. You know, this was the initial wave equation. This was what we have. When we got a equals to 0, it reduced to this, abi? We now got lambda equals to m power over 2, meaning you have this. Are you getting me? So that's it. So meaning this is our general wave equation. From this general wave equation,
these are general.
Yeah, these are general wave equation. Then
What about those E and F?
we get here. Now from here, from this from this general wave equation, this let's multiply all through. What do you have? Sine all into brackets m pi x over 2, right? All into brackets c multiplying b, right? Cos 2m pi t plus d times b sine all into brackets 2m pi t. Any question on this? Where c multiplying b is equals to e and d multiplying b is equals to f. You want to avoid having a lot of constants or having many constants. So we are saying c multiplying b, take it as e, a new constant. D multiplying b, take it as another constant, which is what? F. So meaning from here, I'm having u as a function of x comma t is equals to sine all into brackets m pi x over 2 all into brackets e cos 2m pi t plus f sine 2m pi t. Right? So this is our engine. This is our what? Engine function, and this is our what? Engine value. This is our engine function, right? This is engine function, and this is what? Engine value. Now this engine function, we want to write a series solution for this engine function. Okay, now from here, I said this is our engine function, right? Now, what engine function? What we want to do is that we want to write a series solution for this engine function. You know, n, I'm having n in this engine function, where n is equals to what? 1, 2, 3, 4, 5, 6, 7, 8, right? Meaning that when n equals to 1, you have its n equals to 1 has its own engine value and engine function. Are you getting me? When n equals to 2 has its own engine value and engine function, right? Any number of n you can substitute. They always have their own engine value and engine function. So meaning that you are going to sum all this up at the end, saying you have a series solution, right? But before then, let's apply this initial condition. We are applying this initial condition. I'm having my first initial condition as this, and I'm having my second initial condition as this. So the interpretation of this initial condition is that t is equals to what? 0, right? Just like the way we did for boundary condition. For the first one, we substituted s equals to 0, then we equated it to what? 0. But in this case now, we are giving t equals to 0, meaning that substitute your initial condition into your what? Engine function. You know, this is the first one. It is telling you that t is equals to 0, meaning when t is equals to 0, anywhere you see t here, substitute what? 0. Your answer equate it to what you have here. That's the meaning. Similarly, this is also telling you that differentiate what you have here. By the time you differentiate it with respect to t, your answer equate it to what? 0. Right? So the one we are going to go with first, we are going to go with this first. Meaning that differentiate this. You know, the initial condition given to us is what? U equals to this when t is equals to 0. But this one, the first derivative of u with respect to t is equals to 0 when t equals to 0. Any question on how I interpret this in the initial condition? Relating it to the general format. You know, this is the general way. U as a function of x and t, right? Doing comparison with this, what's t? T equals to 0. Meaning anywhere you see t in this engine value, substitute it to what? 0. You substituting it to 0, equate it to this. That's the meaning. That's for your first initial condition. For this one, it is telling that differentiate this with respect to t and substitute t equals to 0. Meaning your derivative, substitute t equals to 0, then equate it to 0. What do you say? The first one, just like the way we did boundary condition. In this case now, it is telling me t equals to 0, right? Meaning in my engine function, substitute t equals to 0 in my engine function, then equate it to this, right? This is the interpretation. The second one is what? The partial derivative of u with respect to t of this u. When t equals to 0, then equate it to what? 0. Are you getting me? So meaning that we are going to start with this first. We're starting with this. Let's differentiate this. We're differentiating this. I'm having the partial derivative of u with respect to t becomes, what do you say? So we are saying that the partial derivative of u with respect to t is equals to sine all into brackets m by x over 2, right? Now differentiate this. We are differentiating this with respect to t. We call your partial differentiation. Let's differentiate this with respect to t. What do we have? Using chain rule. Let's bring it out. I'm having e cos all into bracket 2m by t, right? Let's treat this e as constant. Say we want to differentiate this. I want to get the partial derivative of u with respect to t. I want to get the what? Partial derivative of u with respect to t. I'm going to say that u is equal to what? 2n by t, right? Meaning that the u over the t becomes what? 2n pi. Then this my original equation becomes what? Cos u. What is the derivative of cos u? The derivative of cos u is what? Minus sin u. Meaning that 2n pi multiplying negative what? Sin u. Right? Where u is what? 2n pi t. So substitute. You have negative 2n pi sine all into bracket 2n pi t. That's it. Any question? Hope you are not confused. What we did was that following this initial condition, just not the second one. Exactly. I'm using this second one just because it is easier for me. The logic is that the one that is equal to 0 starts with that one. Are you getting me? This stated that this is the initial condition. This is the first one, this is the second one. But I'm using this first. Why? Because this one is equating 0. You are equating it to 0. So let's start with 1 equals to 0. If it was this one that equated to 0, I would have started with this. Right? So meaning from here now, following the condition, it is the condition I'm following. The condition is telling me that differentiate this. By the time you've gotten this derivative, substitute t equals to 0, then equate it to 0. So me having this as a function, what do? Differentiate. Me differentiating, I'm going to do partial differentiation to what? Cos 2n pi t. Partial differentiation to what? Sin 2n pi t. So I'm not taking it to chain rule, saying that when I have cos 2n pi t, let's differentiate. I would say u is equal to this, right? Then the u dt, I will have this, right? Then if u is this can be written as cos u. Differentiate cos u, you have negative sin u. Then the derivative of this becomes the first derivative times the second derivative, meaning 2n pi multiplied by negative sin u. Here u is what? 2n pi t. So you are saying negative 2n pi t sine all into bracket 2n pi t. Are you getting me? That's what we just did. So if that be the case, meaning that my second derivative is equals to right? So if that be the case, hope that get what I'm saying. So I'm having, we are not differentiating this. This is a constant. You are bringing this out, multiplying your constant, which is e, multiplying what you differentiated, meaning negative 2n pi, right? Sine all into bracket 2n pi t plus. This is a constant also, f. The way you differentiated this, differentiate this also. So let's differentiate. That will be what? Differentiate sine all into bracket 2n pi t. Let's say u is equals to 2n pi t. The u over the t becomes what? 2n pi. Therefore, sine Therefore, this implies what? Sin u. Differentiate sin u, what do you have? Cos u. Meaning the first derivative multiplying the second derivative, that is 2m pi multiplying cos u. Where u is what? 2m pi t. So you're having 2m pi cos all into bracket 2m pi t. So you've differentiated this also. Back substitute. I then have 2m pi, right? 2m pi cos all into bracket 2m pi t. Close your brackets. So this, the interpretation for this is that differentiate your u. That's what we've done. Substitute t equals to 0, then equate it to 0. Meaning this guy, I'm equating it to what? 0. But I'm going to substitute what? T equals to 0. So anywhere I see t here, what do I have? 0. So let's substitute. With substituting, I'm having the u over the t is equals to sine all into bracket m pi x over 2 all into bracket e multiplying negative 2m pi sine all into bracket 0, right? 0 multiplying this, multiplying this, multiplying this, you still have what? 0. Any question? No question. Plus f multiplying 2m pi cos what? 0. Now, sine 0 is what? 0. Cos 0 is what? 1. Meaning from here, this becomes what? Sine all into bracket m pi x over 2. This is what? 0. This will cancel out, right? Sine 0 is what? 0. All of this is not there again, meaning this has cancelled out. Then I'll be left with what? F all into bracket 2m pi equals to what? 0. Are you getting me? You know, from here, this is 1. So 1 times this, you have this. Any question on that?
Why not sign?
We don't have a t function in it. You know, we said differentiate with respect to t. We don't have t function, so it will be 0 itself. If you want to differentiate this would have been 0. So I'm differentiating with the one that has t as a function. So that's it. So meaning for this initial condition, for this second initial condition, I got u as a function of x t to be what? Okay, now from here, from this initial condition, I've gotten the u over the t is equals to sine all into bracket m pi x, right? All divided by 2, multiplying what? Multiplying 2m pi, right? Multiplying f, equating that to what? 0. Any question? What I have here is still the same thing as what I've written on the board here, right? When we did the boundary condition, we got A and what? B. You know, I said it previously that all these conditions say boundary condition. What's the idea of boundary condition? You want to know this constant, right? When we did boundary condition, we found the value of A and what? B. We found A to be what? 0 and B not equals to 0, meaning we got an engine value, right? That was how we got this. Now I'm having E and F as a function. What does it mean? I have to know this same value also. Are you getting me at all? I'm having E and F, meaning I have to know the function, I have to know the value of E and I have to know the value of what? F. How do you know the value of E and how do you know the value of F? Apply this boundary condition. By the time you apply this boundary condition, you know the value of E and you know the value of F. But note that one of these functions, you know, the idea is that you want to have a general equation. At the end, in your general equation, you have one of these constants left in that equation. Are you getting me at all? You know, how to model a wave equation for a vibrating system. Out of all these constants that we've been eliminating, that we've been getting the value. Check, is it recording? Is it counting? So out of all these constants that we've been evaluating, at the end, meaning our wave equation, we have one of these constants left in that equation, right? So meaning I'm having E and F. Out of E and F, at the end, meaning my wave equation, my modeled equation for the wave, one of these will be left in it. Is it E or F? How do we know? It will be what? Will it be E or F? It's going to be E. Based on what we've calculated here, what the value of f? 0. Are you getting me at all? What the value of f? 0. How is it 0? Divide all through by this. You have 0 by this, which is still what? 0. Divide all through by this. Or this implies f equals to 0. True or false? True. And the idea is that once you've gotten a constant, what do? You substitute back into what you are left with. Meaning you substitute back into your what? The wave equation that you have. Are you getting me? In this case, this was my wave equation so far now. And I've gotten f to be what? 0. Meaning anywhere I see f in this wave equation, what do I substitute? 0. By the time you substitute 0, the whole of this will cancel out. You'll be left with this. And this is your wave equation. This is the model equation for the vibrating system. Are you getting that though? It's just all about we calculating those constants. Calculate A, B, C, D, E, F. So now from here it implies that F is equals to what? 0. So if F equals to 0, the same way you substituted A equals to 0 into the original wave equation, and the same way you substituted engine value into the second wave equation, substitute F equals to 0 into the wave equation you have now. By the time you substitute that, meaning this will cancel out, true or false. So this is what I'm saying. By the time you substitute that, meaning that you are having u all into brackets st, right, sine equals to sine all into brackets m pi x over 2, right, e cos all into bracket 2m pi t, right, plus 0 times sine 2m pi t, right, and this will give us 0. So you are left with what? U as a function of x and t, equating that to what? Sine all into bracket m pi x over 2, multiplying what? E cos all into bracket 2m pi t. 2m pi t. Meaning when I apply the first initial condition, I got my new wave equation to be this. Now apply the second initial condition, which is this. Meaning you are going to have another new wave equation, which is the final equation for that question. This is the final equation for that question. Any questions so far? So meaning this is our engine function. This guy is called the engine. Okay, let me. Okay, now for me, I said this is our new wave equation. From this new wave equation, we call that I have lambda is equals to what? N pi over 2, where n is equals to 1, 2, 3, 4, 5, 6, right? Are you getting me? Where n is equals to what? 1, 2, 3, 4, 5, 6, right? Now, by n equals to 1, 2, 3, 4, 5, 6, meaning that when n equals to 1, it's going to have its own wave equation, true or false? When n equals to 2, you are going to have its own wave equation. When n equals to 3, you have the wave equation. Similarly for any value of n. Are you getting me at all? So with that, we can write a series solution for this wave equation. By series solution, we are saying for any value of n or for all value of n. Right? With what we have on this board. Any questions so far on how we got this and on how we got this? Do you have questions on how we got this? No. So looking at this wave equation, what does it mean? This is, we've gotten this previous, the engine value. So it means that n equals to 1, n equals to 2, n equals to 3, n equals to 4, n equals to 5. Meaning for every value of n, they have their own wave equation. When n equals to 1, the wave equation of when n equals to 1 is going to be different from that of 2, 3, 4, 5, 6, right? Are you getting what I'm saying? So if so with that, I'm not saying that. Okay, to understand what I'm saying. Now, when n equals to 1, let's just do it here. Let's do it here. When n equals to 1, when n equals to 1, right? Let's get our wave equation. Meaning, I'm having u as a function of 1 and t, right? Is equals to what? Sine what? 1 multiplying pi over x over 2, right? E cos all into bracket 2 pi t, right? 2 times 1 times n times t, right? This is when n equals to 1. I said you write a series solution. But let's continue. This is when n equals to 1. When n equals to 1, this is your wave equation, right? When n equals to 2, same idea. What do you have? U all into bracket 2 comma t equals to sine all into bracket 2 pi x over 2, right? E cos all into bracket 2 times n times t, right? When n equals to 3, what do you have? U all into bracket 3 comma t equals to sine all into bracket 3 pi x over 2 e cos all into bracket 2 times 3 times pi times, it should be pi. This is what we are following, n pi t. This is pi. So multiplying 3 times pi times t. Now, what do you observe? This wave equation for n equals to 1, n equals to 2, n equals to 3. What do you notice? They are following same pattern. They are following same pattern. So if you are following same pattern, it means you can write a series solution for it. Where that series solution you can get for any value of n. So your series solution becomes from what we have here. You can still write this as saying u as a function of x comma t is equals to e sine all into bracket n by x over 2, right? Multiplying what? Cos all into bracket 2n by t. Now, you writing a series solution for this, you are saying that u subscript n all into bracket x comma t is equals to e subscript n sine, okay, let me use n1, okay, let's say n, e subscript n sine all into bracket n pi x over 2, right, cos all into bracket 2n by t, where this n indicates for n equals to 1, n equals to 2, n equals to 3, n equals to 4, right, which is still the same thing as you writing in terms of this sign. Okay, let me use another value. Let's say r, so it won't confuse us.
I'm even asking about this x.
Okay. Take n as x. Yes, take n as x. No, not a must. But let's continue now. From here, writing the series solution, meaning in terms of this sign, I'm having my wave equation as what? U n all into bracket s comma t is equals to e summation, okay, is equals to e sine, okay, from here I'm having it as equals to u subscript n all into bracket s comma t equals to e multiplying summation e sine multiplying summation from, okay, let me do it this way, e subscript n, right, e subscript n sine all into bracket n pi x over 2, right, then the summation from n equals to 1 to infinity cos all into bracket 2m by t. Do you get? Meaning when n, what this series solution means is that when n equals to 1, you have this. When n equals to 2, you have this. When n equals to 3, you have this. So for any value of n, you have to stop. This is your general wave equation. This is your general wave equation. Now, it's part of the question now. You have to solve it like this.
You have to write the series.
What we did here, don't get it confused. What we did here, up to this level, any question, you don't have question, right? Now from here, and we said n equals to 1, 2, 3, 4, 5, 6, right? By the time you substitute n equals to 1, you have this, right? N equals to 2, you have this. n equals to 3, you have this. You will now notice that all these guys, they are following the same pattern. The difference is that I'm having 1, 2, 3. This one, I'm having 1, 2, 3. So meaning they are the same. You can write a series solution for it. By series solution, this is what we are saying, which is still the same thing as this. We only included this side. From here, this is it. We got the series solution from here, where n is equals to 1, 2, 3, 4, 5, 6. Then you can actually leave it like this, but then to just indicate that we have infinity, meaning 1, 2, 3, 4, 5, 6, 7, and the like. So this is how you write it. This is how you write it. Now, this is, these ones, we got this from what? Our second boundary condition, our second initial condition. Now, let's use this first initial condition. Let's use first initial condition. We're using first initial condition. Let me pause that video. Hello. Are we together? Now let's finish up with this. Let's finish up. Now, when we started, we said we made use of the boundary condition and what? Initial condition. When we use the initial condition, for those boundary conditions, for the first boundary condition, we have a wave equation, right? Hello. For the first boundary condition, we have a wave equation. For the second boundary condition, we obtain a new wave equation, right? Similarly for this initial condition too. For the first initial condition, we obtain a new wave equation, right? I hope I'm communicating. Now from here, I said for the first one, for the boundary condition, for the first boundary condition, we obtain a wave equation, right? For the second boundary condition, we also got a wave equation, right? Now, similarly for initial condition, for our first initial condition, we got what? A wave equation. We obtain new wave equation, right? Which was this. Now, this second boundary condition, we got this, right? This was what we got, and we equated this to this, following the rules. So what this means is that what I said. Any question up to this level? We've gotten this already. We equated what we have here to this. Now, what this is telling us is that it is telling me that En sine, from here it is telling me that En sine n pi x over 2 is equals to 6 sine n pi x. So this is equation 1. Then the other one, I'm having En sine, all into brackets, n pi x over 2 equate that to what? Negative 3 sine 4 pi x, right? You don't include the summation. This summation is telling me that when n equals to 1, when n equals to 2, when equals to 3. But when we have something like this, we are saying that this is equal to this, and this is also equal to this, right? Now, the interpretation from here, say this is equation 1, say this is equation 2. From equation 1, I want to know the value of n from equation 1. This is my final wave equation. So from equation 1, I want to know the value of n that gave me 6 sine n pi. Are you getting that? We've seen that n equals to 1, n equals to 2, n equals to 3, n equals to 4. This is the series solution. Now for this particular one, saying that this is equals to this, and this is equals to this, given from the boundary condition. So what I want to know is that I want to know the n, the value of n that gave me this, and the value of n that gave me this, right? Now doing comparison between what I have here, I'm having, for this first one, I'm having, this is it, I'm having En sine, all into brackets, n pi x over 2, equating that to what? 6 sine pi x, right? This is the first one. For this first one, what does it mean? It means En is equals to what? 6. So I want to know the value of n that gave me 6. I want to know the value of n that gave me 6. So from what I have here, meaning sine, all into brackets, n pi x over 2 is equals to what? Sine pi x. Observe that sine cancel out. I'll be left with what? N pi x over 2, equating that to n pi x. Equating that to what? Pi x, right? In this case, what do I have? This pi cancel out, n cancel out, right? S cancel x. By the time you cross multiply, you then have n equals to 2. Meaning when n equals to 2, you got en to be what? 6. You got en to be 6. Similarly, for your second equation, saying e subscript n sine all into bracket n pi x over 2, equating that to negative 3 sine 4 pi x. In this case, what do I have? E subscript n is equals to negative 3. Sine cancel sine, right? I'll be left with what? N pi x over 2 equals to what? Equals to 4 pi x. Sine cancel sine, E subscript n equals to negative 3. I want to know the value of n that gave me en to be negative 3. So from here, this also cancel out, right? By the time you cross multiply, what do you have? N equals to 2 times 4, which is equals to 8. Therefore, when n equals to what? 2, I got en to be what? 6, right? When n equals to 8, I got en to be what? Negative 3. Negative 3. So now, to conclude with what we have here, you now come back to this. You come back to this saying that your final solution becomes what? U all into bracket s comma t, equating that to, you are working with two equations now. The first one is when n equals to 2, right? While the second is what? When n equals to 8. U all into bracket s comma t is equals to sine all into bracket 2 pi x over 2, right? All into bracket, what's my en becomes what? 6, right? Because all into bracket 2n, okay, 2 times 2 times pi times t, right? This gives me what? 6 sine pi x, right? Cos 4 pi t. Any question? When n equals to 2, e subscript n equals to 6. That's what we substitute into this general equation. Then we got this. Using the second one too, what do we have? Meaning I'm having u as a function of xt is equals to what? Sine all into bracket 8 pi x over 2 multiplying what? What's e? Negative 3, right? Cos all into bracket 2 times, what's n? 8. 2 times 8 times pi multiplying t, right? This becomes what? Sine this becomes what? Sine 4 pi x, right? Okay. By the time you do this, I have negative 3 sine 4 pi x, right? Cos 16 pi t. So this is our final equation. Therefore, u as a function of x and t is equal to this first one, which is what? 6 sine pi x cos 4 pi t minus 3 sine all into bracket 4 pi x cos all into bracket 16 pi t. 16 pi t. So for that question, this is the general wave equation. So this is what we've been calculating so far. This is our answer. So this is our answer. So given a question, just understand what the question is. Understand your initial condition, understand your boundary condition. Then implement your boundary condition, also implement your initial condition.